You will notice that some of the coefficients in these particular examples are specially tuned. Well, this is because I'd like the final expression to be as not as cumbersome as they could be. So technically, you could change these coefficients and the whole procedure stays the same, but the answer would be much more cumbersome. That's it. So here is our first differential equation. So we start our solution with their P and Q polynomials composed of the coefficients of our equation. So let's construct P polynomial. It is composed of the coefficients which don't contain z variable. So here is -2 and here is 1. So the P polynomial is going to be -2t plus 1. Now the Q polynomial. Well, it is composed of the coefficients which contain z. So this one, which is 1, so it's t squared. And plus this one. This coefficient is -1, so it's -t. Now we need to compute the integral. So let's factor out minus sign. Right, so what you notice is that the numerator is a simple differential of the denominator. So it's simply minus d over t squared minus t divided by t squared minus t. And the answer is a simple log. Right, now we may compose z function which enters our exact solution. And as you remember, it is defined as follows. It's 1 over q times e to p over q dt. So the integral gives us the simple log. So the exponential to the log will just give us t squared minus t in the denominator. And additionally, we have t squared minus t from this q polynomial. So our z function is t squared minus t squared. Right. And our v function is q times z times e to xt. Right? So, and what we get is simply e to xt divided by t squared minus t. Well, actually, to make things a little bit simpler, let's factor out t in the z function and t in our v function. And the solution is presented by a general integral. Right. So now here comes the most interesting part of that kind of problems, namely the choice of the contour. Well, first we plot the complex plane of variable t. Next, we need to have a closer look at our v function. So what do we see? V function is a single-valued function. It has singularities at point 0 and 1. So what would be the possible choice of the contour? Well, since v is a single-valued function, any closed contour will do. But the problem is that, for example, if we choose this closed contour arbitrary, then you see that u function, the integrand which defines u function, namely z function, doesn't contain any singularities inside this contour. And that means that the closed loop integral will simply give us 0. It's an integral of analytical function inside the closed contour. U is equal to 0, of course, is the solution of this differential equation, but it is of no interest to us. So in our case, in order to get the reasonable non-trivial answer, our contour can be still closed, but it should circle around some singularities. In our case, if you look at the integral, you see that those singularities are just poles, right? Second order poles at point t equals 0 and t equals 1. So why don't we choose two contours, each of which circle around particular pole? For example, let's call this contour gamma 1 and this gamma 2. As you see, well, since each of these poles contain, each of these contours contain a pole inside it, the integral which defines the solution is not going to be equal to 0. So it defines some non-trivial solution. And both of these contours can't be smoothly deformed into one another. That means that they define two linear independent solutions. You can technically choose, for example, the contour which circles around both poles. But as you have already guessed, this contour can be decomposed into the combination direct sum of these two ones. So the solution defined by this general contour will be a simple linear combination of these two linear independent solutions. Let's compute the first one, the solution defined by the residue at t is equal to 0. So u1 of x is equal to some constant c1 times the integral over contour gamma 1 the integral is reduced to their computation over second order residue at the corresponding pole. Which is reduced to first order derivative. The derivative of exponential brings us additional x into the numerator. And what you get is simply x times, and of course you should compute this at point t is equal to 0. So what you get is x times e to xt at t is equal to 0. So it's simply x divided by -1 squared. So it's just x minus 2 over t minus 1 cubed, which simply gives you -1 cubed. And then times e to xt at t is equal to 0. So this is the first solution of your equation. So it's simply x plus 2. Okay, let me check. Great. Let's now find another one. So u2 of x is simply equal to c2 times a very similar integral, but taking along the second circle. Again, it's a second order pole, so the whole solution is defined by their first order derivative of their integrand taken at point t is equal to 1. All right, so and what we get is, again, once you differentiate the exponential, you get x times e to x minus 2 times e to x. So we can factor out e to x, and we get the second linear independent solution. Let me check. So now we get the full answer for this differential equation. So it's a linear combination of two functions. The first one is basically x plus 2, and the second one is e to x times x minus 2. So that's it for the first exercise. As you see, as you notice, it's the answer is a combination of two elementary functions. Well, this is a rather an exception, I would say. In most cases, this integral, the integral which defines your solution, can't be taken exactly, and the best you can hope for is to find some reasonable asymptotics of this solution, and this will be discussed in our second example.